Okay, Physics 122 students, let's go through exam number 3 and grade yourself here and look for your mistakes. This will give you an idea of how you did. I'll grade this as quickly as I can and get it back to you. But more importantly, it'll see if you made any mistakes or where you made the mistakes, and then, you know, what you did wrong. And learn from those mistakes here. All right, so let's start with number 1. You can kind of see it's going to be Ampere's law. It says, using Ampere's law, what is the equation of the magnetic field as a function of r being distant from the center, inside a wire with a circular cross-section? If, and we got, looks like 2 parts here. And the easy one is the one we did in class. If the current density is uniformed, that is, there's some current density just equal to a constant 5. Okay, well, if it's just equal to a constant 5, then we would have something that looks like this. Let's see, Ampere's law. It says, if you add up the magnetic field around a loop, you're going to get permeability of free space times the current that is inside that Amperean loop. So the diagram helps us a little bit. Let's look at the little loop here, because that is the one that's inside the wire. Looks like we won't need the bigger loop because both of these are asking for inside of the wire. But then notice then that the current is what goes through the Amperean loop. So I'll just kind of color in the part that goes through. So that would be, it would not be the total current of I, but it is going to be related to the density here. And so like we did many times in class, the argument goes something like this. First take the dot product and argue from symmetry that the angle is 0. Again, we see that because you can kind of imagine yourself standing anywhere on here, and therefore the magnetic field must be perpendicular then to an axis of anti-symmetry. We also argued then that because of where you stand on it, around the ring has the same symmetry. Oh, I'm sorry. We take the dot product, it's first ds, getting ahead of myself. But, guess trying to go a little too fast here. We did this argument quite a few times in class. So let me just jump to the symmetry arguments, or past the symmetry arguments, and say angle's got to be 0, b's got to pull out, integral of 2s would be the circumference, which is 2 pi r. Now, the other side of the equation then would be mu naught times the current that is inside, and I'm going to do this. Now, I must admit, for A, thinking of it as an integral is not really necessary. Because it's just current density times the area, and the area would be the area enclosed by the Amperean loop, so it would be pi little r squared. And then once we do that, we can see that there's an r on each side, there's a pi on each side, and so we get b is equal, and it looks like we've got the 5 times the mu naught times the r over a 2. And I'm just kind of thinking what we got in class. We got it proportional to r, and that's true. I don't know if we want to simplify this to 2.5 mu naught r, but maybe I will. And I would think that during the exam you'd kind of look at, this must be section 330.3, and you're going to then see what do you have in that section? I think it comes out to be B equals, and you get the 2 pi r, the mu naught. Oh yeah, and then you get the total current. I don't think this is going to help us, and you get a little r over a big R squared. Big R being the radius. Well, maybe that helps, because you could look at this then as mu naught, and then one of the r's cancels off, but this current divided by pi big R squared would be current per area, so that'd be the current density, which in our case is the 5. You still have the R, and you still have the 2, and that's exactly what we got. All right, so hopefully this wasn't the hard one, but hopefully thinking of it in terms of current density sets us up for the second part, which is the harder part. It says if the current density changes, it has a decrease going from the center out, and it's in the shape mathematically of a Gaussian function, and they give us the function. So not worrying about really what the name is called. We just have to do the math behind it. And so kind of doing the same thing, starting with Ampere's law, integral of B dot ds would equal to mu naught times the current inside of our Ampean loop. Again, kind of rushing through the symmetry arguments again. This would be B times 2 pi r mu naught. But this then would be the current density times the area. And then this one gets a little bit harder, because if I maybe kind of redraw a cross section, so here's the wire. Here is the Ampean loop. And what I would want to then do is to add up all the current in like a series of very thin shells. I guess it might look something like this. I would have this question about, how much current goes as it comes towards you in this shell, but then add to that how much current is in a shell, that's kind of wrapped around it. And so I'll take a little current there, plus a current there, and then maybe do that a third time. And then, of course, ultimately, we would do it an infinite number of times. And so I'll take the current here and this one, plus the current in that one, plus the current in that one. And we'll start off at a really tight radius and then just add it all the way up. And so what I'm getting at is I would then take the current density that changes with r, and so according to this equation, it's 5 times e to the negative r squared. And then I would have to take the area of one of these, and it might be kind of hard to see the area. This is so thin. But if I take a ring here, the area would be its circumference, 2 pi r, and its thickness would be a dr as I'm adding up from the smallest one out to the biggest one. And so there's kind of the hard piece. And then luckily, this has a perfect u sub. So it's not a hard integral. And so maybe just setting this up is the hard part of this. All right, so then I've got b 2 pi r still over here on the left-hand side. And then over here on the right-hand side, why don't I go ahead and factor out the 5 and the 2. That makes a 10. I'll even factor out the pi. And now I'm just left with an integral of e to the minus r squared r dr. And since this is the derivative of that, or differential, it's a perfect setup for a u sub. So if I let u equal to r squared, du becomes 2r dr, or 1/2 du is r dr. So I'll go ahead and I got the mu naught, I got the 10 pi here. But right here with this integral, I've got e to the minus u now. And then the r dr is the 1/2 du. And I'll just then take this 1/2 on out and call it a 5 pi. And then I just got an integral of e to the minus u du. Now again, lucky for us, this is a very easy integral to do. Integral of e to the minus u, well, of course, is itself with a -1. And the negative comes from the chain rule. I like to kind of double check by saying, let's take the derivative of that and see if we get back to here. So the derivative of e to the negative u, of course, is just e to the negative u, and then the chain rule will give me a -1. So that would cancel off. And in fact, maybe I'll just put the negative here for a second. And then I just have an e to the negative u, which I will now switch back to what u is equal to, which is r squared. And with that in mind, I can go back to say what were my limits, and I originally wrote them right there, 0 to r. Okay, so this would be minus mu naught 5 pi. And it looks like I would have e to the minus r squared minus an e to the 0, which of course is a 1. And then if you'll let me take this, this would be a 1, but incorporate that negative so that this becomes a 1 minus e to the minus r squared. Nice. Okay, now bringing the other pieces over, I can finish this and saying, okay, let's bring the 2 pi r on over, and we'll have the mu naught, we'll have the 5 over the 2, and the pi will cancel. And then this would be 1 minus e to the minus r squared over r. Or maybe the very last step is to simplify this to 2.5 mu naught. And the numerator is 1 minus e to the minus r squared. And in the denominator is r. Yay! And that's the hard one. And it looks a little bit like this one. in some sense. But obviously the arc coming over here, a little different. Nice. Well, I was just going to say, if we want to do a Taylor series, we can kind of test this out. But let's call that good and move on to number 2. So there's the first problem. Let's go on to number 2. Now, number 2, it has a toroid, so it looks like a little bit from chapter 30, but it looks like it goes on to say what's the EMF, and actually the maximum EMF. So it looks like we got a Faraday's law here. So Faraday's law says that the EMF is minus the number of turns in the secondary times the time derivative of the amount of flux, magnetic flux, the change in the magnetic flux that goes through the secondary. So here's our little picture. We have a toroid, and the toroid has 250 turns. It gives us an inner radius of 3 centimeters, and then a rectangular cross-section that's kind of listed here as an A and a B, a 1 centimeter by a 2 centimeters. It gives us a current with that very famous angular frequency of 377. That's our 60 hertz cycle. And it says, what's that maximum EMF? And so let me kind of put these numbers in. The number of turns in the secondary is this N prime, which is 50 turns. Okay, good. Now, the flux is needed to take first this dot product between B dot dA. And looking at and remembering the direction of the magnetic field in a toroid, the tunnel part of the toroid wraps around, and that's going to hit the surface of the secondary kind of flat on, or in the same direction as the normal. So that's where the cosine of 0 comes in. And of course, the magnetic field in the toroid is the number of turns in that toroid times mu naught times the current over 2 pi r. And so there is our magnetic field. And then notice this magnetic field is going to vary with time because the current varies with time. But it's also going to vary with position because the field from a toroid, as we learned, is really strong near the inner radius and then tapers off and gets a little weaker towards the outer radius according to this 1 over r pattern. So maybe in kind of a green color here, I'll make like a little strip and say that, okay, the area that I need to add up is a bunch of these little strips, which I will say each strip has a height of A, and then the thickness of it is dr. And so when I go to add up the flux, the magnetic flux, I would be started at an inner radius of capital R and continue on until I went to a distance B from the inner radius. And so the outer radius would be R plus B there. And so now I can kind of simplify some things. Maybe I'll start with this N, which represents how many is in the toroid. So I'll pull that all the way out. Also, the mu naught is the 4 pi times 10 to the minus 7. Now, the currents kind of get stuck here at the time derivative. At some moment in time, it's a constant in space. And so as you take a flash picture in time and say, okay, where's the current? The current's the same everywhere in space, so I can take the current in front of the integral with space, but not in front of the derivative of time. And so that's those three. Now, A can be also pulled out, and I think A was, 1 centimeter? So 0.01 can be pulled all the way out in front of the integral and the time derivative. And then likewise, 2 pi can be pulled out in front of the integral and the time derivative. but it has to stay within the integration. And that's the only thing that has to stay there. So I'll do that integration. Now let's see what we have here. So we've got a 50, we got 250. When I save myself a little work, and notice that the 4 pi and the 2 pi results in 2 times 10 to the minus 7. There is the height of the toroid. That's the 1 centimeter. Let me leave the derivative of the current alone for just a second. And this then becomes ln, and then it would be r plus b minus ln of r, but I can write that then as a quotient. And so I'll take advantage of the properties of logarithms and do a quotient. And then this r, I believe it was a 3 centimeter. Yeah, 3 centimeters. And b is 2. So there's a total of 5 centimeters. And so that would be the r plus b in the numerator, and then the 3 in the denominator, which is the same as just 5 over 3. And it doesn't change with time, so it can go in front of the time derivative. So let's see. So we've got a 50 times a 250 times a 2 times 10 to the minus 7 times a 0.01 times a natural log of 5 over 3 when I bring that in front. Now, my last step here, take the derivative with respect to time and of current. And so there'll be a 5.25, and then this would become now a cosine of 377t with a chain rule of 377. So there's the maximum current, and then there's the angular frequency, and then there's the cosine. And of course, it's not a surprise that as the current changes with time in a sinusoidal pattern, the voltage is going to change in a cosinusoidal pattern. It's going to be out of phase. And when we were here in chapter 31 doing Faraday's law, we haven't did our circuits yet, but now that we went into chapter 33 and I did our circuits, we learned the whole Eli effect, where the current and voltages are not in phase, but they're out of phase by 90 degrees. And so if one's a sine, the other's a cosine, then not worrying about pluses or minuses. Anyways, to finish this problem, it does say the maximum. And so this would go up and down, and then this would be its amplitude. And of course, I should say it's a minus cosine function. But at some point, this then, at some moment in time, this is going to be a negative 1 going with that negative, making it that is its maximum. And so its maximum is all these things multiplied together. And so I will just say EMF max and ignore the negative, or maybe I shouldn't say ignore it. Associate the negative with when the cosine is a -1, that's when it's going to get a positive, and it's largest. So now I can finish up the problem by saying, all right, what is 50 times 250 times 2 times 10 to the -7 times 0.01 times a natural log of 5 over 3 times a 377 and times a 5.25. And I would get a maximum of 0.0, I'll call it 253 volts. Yay! And so there's question 2, Faraday's Law, chapter 31. So I guess this was Ampere's Law, chapter 30, Faraday's Law, 31, which, not a surprise, chapter 32, which is DC circuits and inductors. So here we have an inductor. It looks like 2 resistors. Let's study this because it says study the circuit as shown. Okay. The switch has been closed for a long time. Now that should trigger our discussion about how does an inductor behave in a short time and a long time. Well, in a short time, it produces a back EMF that's exactly equal to what's ever pushing it, and so the current is 0. Or if it had started with a current, it remains at that. It doesn't really like to change. That's the whole Faraday's Law. And in this case, if you were closing the circuit, I would have to say, if it had been opened for a long time, there probably is no current in here. So as soon as you close it, there'd be no current. Now, that's not relevant for this problem. This problem says it's been closed for a long period of time. So for a long period of time, things have settled down. And we know that the voltage on an inductor is minus L di dt. And so after a long, long period of time, there's no more changing of the current, so there's no more voltage. And so we can just think of this as kind of a straight wire, And so basically, all I have is a 6-volt battery that comes off and then 2 resistors in parallel, some of the current going around this way and some of the current going around that direction. And if I did a little loop over here on the left, a loop starting here, which is, you'll see I'm going to need here for A, I would go plus 6 and just treat that as a wire. And then I'd go minus I1 R1, which is 100, and complete the loop. And bottom line is I would get current number 1 as 6 divided by 100, which is 0.06. And not a surprise. I mean, this would go all the way back to chapter 27. I just have, a battery and a resistor, and it's just Ohm's law. And so at this point, the inductor isn't doing anything other than some current flowing through it. And so that's how many amps I have. Well, finally, the part that's relevant for this chapter 32 is that it asks for how much energy is stored. And we said that the magnetic energy would be dependent on how much current there is. According to this equation, it depends on the inductor and also the current squared. So in this case, it's just 1/2, and then we've got 25 milli, and the current is 0.6 amps squared. Now, if we want to double check this with our units here, the units for the inductance is a Henry, and a Henry is a volt per amp each second. So in other words, 1 Henry would mean you have an inductor that would give you 1 volt when the current is changing at a rate of 1 amp per second. So there is the Henry, and then of course we have amps squared. Now, looking at just the number for a second, 1/2 times 25 milli times 0.06 squared would then be 4.5 times 10 to the minus 5. And if you simplify this a little bit, this 1 amp here is going to cancel. And so on the top, you have a volt times an amp. This compound fraction brings the second to the top. Now, a volt times an amp, this would be like current times voltage, should give me power, should give me watts. I suppose you can see that if you remember that a volt is a joule per coulomb, and an amp is a coulomb per second. And then times that second would allow the coulombs to cancel off, the seconds to cancel off, and we can finish the problem by saying this is the energy in units of joules. Okay. So there's the first part, and perhaps the easiest part. Although this is second part's pretty easy if we use our notes here of what we were offered for in class. It says here, what is the current in the inductor 0.2 milliseconds after the switch is opened? So now that the current has been established, and we know that it's 0.06 amps, the current wants to continue. And that was our argument about inductors. Inductors are based upon Faraday's law. Faraday's law says they oppose any change. So if it already has a current of 0.6, as soon as you open the switch, it will create enough voltage. That's what this is, because the current's trying to change. And the more quicker you try to get rid of the current, the more voltage it makes so that it doesn't get rid of it. And so that's why we like to say that it's a continuity here. It creates its own power. It keeps the current going at that same level. So the mathematics we worked out here was that an inductor, when it is being de-energized, would have some initial current and then decay away with this exponential decay factor. That's what we got when we added up the loop. Let me not do all that math again, but it would look something like this. You would have the voltage, here. Well, that's with the switch opening. When it's closing, I guess you wouldn't have a voltage. You would just have the voltage from the inductor and the voltage from the resistor, or in this case, and this is what I want to emphasize, it's going to go around through this second resistor, equals 0. And let me not resolve that one, but hopefully you'll remember this straight from your notes and say, okay, this is the inductor as the current is decaying away, where the time constant tau was the inductance divided by the resistance. And so part of what makes B challenging is you got to kind of remember all of this and then have completed A successfully to get a current of 0.06 amps to begin with the initial current. The time would be the 0.2 milliseconds. The time constant for this LR circuit we need to calculate. And the inductance part is pretty straightforward. It is just given right at the beginning, 25 millihenries. But the thing to catch here is that when you open that switch, the current now will start to process itself all the way around the big loop, going through resistor number 2. And since R1 then flows into R2, this is a series, and you can think of them as one resistor of 150 ohms. And that, of course, 150 ohms we got by adding two resistors in series. And thinking of it as one, this is why this equation that we derived for de-energizing an inductor would be valid, because once we think of those two as one, we just have one resistor and one inductor, and that's exactly that relationship. I'll do the numbers and then kind of the units just to kind of have fun with this again. But remember what a Henry is. A Henry is a volt over an amp per second. So numerical-wise, if I take this 25 milli and divide by 150, I'm looking at a 1.667 times 10 to the minus 4. And it will come out to be seconds. Maybe I should take a moment and show you, let's see, this right here from the Henrys would be a volt over an amp per second. And then this ohm, if you kind of remember Ohm's law, the resistance is a volt over, or voltage over the current. So this would be a V over an amp. I would have let the amp cancel and the volts cancel, and then that per second down here would flip and give me seconds. So sure enough, comes out in units of seconds as it should. So back here, this would be a 1.667 times 10 to the minus 4 seconds. Oh, it looks like I dropped the minus sign there. All right, so 0.06 amps times E, and the units of seconds would cancel off, minus, and let's just see what this comes out to be. This is 0.2 times 10 to the negative 3 divided by the last answer, and so that's a 1.2. So then if I go E to the negative of the last answer, 30%, so 0.3. So I've got 30% of my 0.06. And so we're looking at 0.0181 amps, or if you want, 1, 2, 3, we can write this as 18.1 milliamps is what it will have decayed down to from our, I guess that'd be 60 milliamps. All right, and that would be the answer to number 3. And then, not a surprise, going to chapter 33, where we start working with AC circuits, and then we have the combination of inductors, capacitors, and resistors together. We have this circuit. Now, this is a little harder circuit. We kind of looked at inductor, capacitor, and resistor together, but it looks like what we have now is a second inductor, a second capacitor, and a second resistor. Now, fortunately, they're all in series for us. And so you might just want to think about the total inductance, the total capacitance, and the total resistance. Because even though they're not right next to each other, they're still in series. And so maybe I'll start with the order we learned them. Resistors in series, you just add. So I would say that the equivalent resistance of this circuit is one resistor of 200 ohms. Then we went on to capacitors. Capacitors had that reverse effect that they were in series. You'd go 1 over C1 plus 1 over C2 equals its equivalent. But in our case, the C1 and the C2 are the same. So I could just call it a C and then add the fraction and get 2 over C and then take the reciprocal. So the equivalent would be the C cut in half. So it looks like these two are 40 microfarads. The equivalent, or the equivalent, the EQ of the two is 20 microfarads. And then inductors, we learned, behave like resistors that you just add. So I will just add 330 to 330 and get 660 millihenries. Okay. So moving forward on this problem, I'm going to think of this AC circuit like we derived in class, where we had just one inductor, one capacitor, and one resistor. And that's really what I have. So when it says study the circuit, that's kind of what I'm thinking. Because now I'm going to apply this voltage. And so it looks like kind of a wall plug in North America. It peaks at 170 volts, has an angular frequency of 377, which means its frequency is 60. And there's some phase, because the voltage may not be in phase with the current. And so we wrote the voltage as being out of phase compared to the current, and then the current would have something that would look like this, some maximum value, sine omega t. And that's the question. What is the current in the circuit? And this long analysis said that the current here, maximum, is the maximum voltage divided by the impedance. And the impedance being the total opposition in this circuit. That means it includes the resistance of the resistors and the reactance of the capacitor and the inductor. So I'll calculate this, but I got to get that impedance first. And so why don't I do this? What is the reactance of the inductor? And what is the reactance of the capacitor? And as I already said, I already have the resistance. So let's take and go the 377 times the equivalent of 660 times 10 to the negative 3. And it looks like 248.8 ohms is the amount of reactance or opposition we get from the inductor. Whereas the capacitor, let me take the 377 and multiply it by the 20 micro, and then take its reciprocal, and it looks like I'm at 132.6 ohms for the reactance of the capacitor, because the impedance, as we learned, would be a combination of the effect from the resistor and the reactance of each of the inductor and the capacitor that are fighting with each other. So we got to subtract the two and then square it. So we got to combine the effect of the inductor and the capacitor, that is the reactance with the resistor, and the two of those together is called the impedance. And so mathematically, this would be 200 squared plus 248.8 minus 132.6 quantity squared. And this would be the total effect, if you will. So 248.8 minus 132.6. And so the two of these together is about, well, less than the resistor. It's about 116. Let me square that and add it to the 200 squared. And then finally taking the square root. And so the overall effect is about 231.3 ohms worth of opposition, if you will. And so there is my impedance, which means now I can finish kind of what I was starting up here, that the maximum voltage is 170, and the impedance is 231.3. So 170 divided by the last answer. And we're looking at about 0.735 amps for the maximum current, which isn't quite what they're asking, but it's a good start. Because it says here, what is the current in the circuit when the voltage from the power supply is 0, but is also increasing? Now, the reason that's relevant is right here is the equation for the voltage. So if we were to set this equal to 0, so if we were to say V equals 0, then we are essentially saying the sine of 377t plus the phase is 0. And as we study our sine functions, you get 0 on the sine function when the argument is either 0 or pi or 2 pi or 3 pi or 4 pi or 5 pi or 6 pi. So any multiples of pi. But it's also cyclic, so we don't have to look at these higher multiples. And so we could either talk about 0 or pi, because 2 pi would be the same as 0, and 3 pi would be the same as pi. But another part of this, it says the voltage is increasing. So the key here is they're saying that this whole argument, 377t plus phi is equal to 0. See, for me to get the current, I need to know its maximum, which I have right here. But I also need to know at what moment in time. And that's where this is going to come into play. This is saying that the 377t is negative of the phase between the voltage and the current. So continuing on with what we learned in chapter 33, because not only did we look at the impedance, but we also had the phase. We said the tangent of the phase was, again, the inductor and capacitor competing with each other divided by the resistance. And so knowing these numbers, on the numerator here, I can again go 248.8 and subtract the 132.6. So there's my numerator. When I divide that by the 200, that is tangent of phi. So now I need to go the inverse tangent to get a number. And that may or may be in radians, or that may be in degrees. I suppose it... I'm in radians. Okay, good. And that's probably what I'm going to prefer here. So I'm going to put 0.5. Oh, that's a nice one, actually. 0.526. Isn't that's got to be pi over 6. That's got to be 30 degrees. But I'm going to leave it in radians. Either way, it doesn't matter, because as long as I stay in either radians or degrees, I'm going to do nothing more than take that and put it into my sine function. Because my last step here for this problem is to say then the current at this moment in time would be this maximum, so 0.735. So there's its maximum. Sine of omega t. Well, remember, the omega t is right here. It's opposite of the phi, and the phi's here. So this is negative 0.526. So I can go sine of negative the last answer, which is in radians, but like I said, that's fine. As long as I didn't change it, I'm good. And so that's now a negative of a half. Yeah, that's right. That'd be 30 degrees, because the sine of 30 degrees is 1/2. And this would actually be negative angle. So, yeah, so sine of 30 degrees is a half, and a negative angle would be negative a half. Okay, good. And then, of course, times the original current, which is 0.735, gives me a current of negative 0.369 amps. Yay! And so there's our kind of hard AC circuit or we've got our impedance, our reactance, our resistance, our phase angle, and then a little tricky part about them being in series, and another little tricky part, if you will, of getting the phase to them. That was a good one. Hope you did well in that one. Kind of long there. All right. And now to the last chapter, the one that I said that I'll give you a couple things and maybe it'll make sense to you. Hopefully they're pretty straightforward. E is going to make you think a little bit. But A, B, C, and D were the ones that I kind of said at the end of the class, hey, these will be good ones to put on the test because they're just kind of straightforward, and we didn't have enough time to do justice on this chapter. And it gives a little background to the S-band. NASA developed communications for the Apollo mission. Here's the radio waves. You're going to send them out from Earth to the moon or to wherever Apollo is. It's not quite all the way to the moon yet. But from Earth to the moon, NASA uses a frequency of, and so we're at about 2.12 gigahertz. And so if we're, say, looking at Earth and moon, here's the line going from the Earth to the moon. And I say in here, call this the Z-axis. And so that means if I'm making a grid, we might do that, the X, let's see. So we have to go X cross Y and give us a Z. I know normally we like to call, but I kind of got myself pinched into a picture there before I read this was the Z-axis. But a lot of times we like to call the horizontal the X-axis, up the Y-axis, and then kind of coming out of the paper here, the Z-axis. Mine's kind of doing this, where I'm kind of taking this Y-axis and pulling it down to the Z, and then at the same time taking the X-axis and pivoting it up. And so this Y comes down to here, the X flips up to there, and as the X is flipping up, this would, well, by that time, by bringing the Y down, the Z would be down, and so as the X flips up, the Z would flip up, and so there's my Z. So there's my grid. Whether you want to look at it like this or like this, I guess doesn't matter. Maybe I should go back to this one. But there is the direction that it travels. It also goes on to say that the maximum electric field, and it gives you a value, and it says it's in the Y direction. Now, what's important about this is really kind of the answer to A, is what is the direction of the magnetic field? And so the layout that we learned by doing a bunch of math, and I said you don't have to really kind of repeat the math on the exam. It is a lot of math, but the math did show us that the three things, the electric field, the magnetic field, and the direction that energy travels, the direction that it moves, in other words, form a three-dimensional layout. So if it's traveling in the Z direction, the fields have to be in the XY direction. And so they're saying the electric field is in the Y. That would mean the magnetic field would have to be in the X direction. Maybe a little more technical, you might argue the negative X direction. Because we also said that you have to go do a kind of a right-hand rule from the electric field to the magnetic field. Because if you did it the other way, magnetic field to electric, you get an opposite direction. But from electric to magnetic, you get the direction it travels. So if the electric field is in this y direction, then magnetic field would have to be in the negative x direction. So when I do a right-handed rule, I would get my thumb pointing in the z direction, which they say is the direction to the moon. So, like I said, a little more accurate would be negative direction. But since these are waves that oscillate, what's going to happen a moment later is the electric field is going to be in the negative y direction, which then also the B field is going to be in the positive x direction. So again, you get the E cross B traveling in the z direction. So the E and B change direction. So it depends what you mean by the y direction. If you literally mean it's all at that moment in time it's positive y, then in that moment of time it's negative x. But I'll be very generous with this. You just put x direction, and I think you got the right idea. And full credits. But like I said, if E field is positive, at some moment, the E field is positive y, the B field would be negative x. Yet a moment later, the E field is going to be negative y, therefore the B field is positive x. Okay. And so there's the first one, the 3D kind of layout of the electromagnetic fields. What is the wavelength of these radio waves? Well, wavelength we talked about in terms of their velocity divided by their frequency. The thing to remember is their speed is the speed of what we call electromagnetic waves. It is the speed of light. It is what we calculated in class to be 3 times 10 to the 8th. And of course, how we calculated it was part of the permeability and permittivity of free space. That's where we're going to have a discussion in part E of this. The frequency is the 2.119 giga, means 10 to the 9th. And so these wavelengths are 3 times 10 to the 8th, and we will divide it by 2.119 gigahertz. And so we're looking at about 14 centimeters, 0.142 meters. And so there's our wavelength. C is how long does it take for these radio waves to travel from, and so here we'll communicate from Houston to the moon. And of course, this is just the straight up physics, chapter 3, physics 121, distance, speed, and time. And so time would be distance divided by their speed. And again, we're back to like B, what is their speed? Well, these are electromagnetic waves. They depend upon the electric and magnetic field interacting with each other. So they're a combination of the permittivity and permeability of free space. And so in our case, this distance is 3.844 times 10 to the 8th meters. And the speed is 3 times 10 to the 8 meters per second. So you can see here, it's a little bit over 1 second. So 1.844 times 10 to the 8th divided by 3 times 10 to the 8th gives me a speed or a time of about 1 1/4 is kind of the standard thing we like to say. For any of you who might work with ham radios, you know this is the common 2.5 seconds. You send it out, you bounce it off the moon, and come back, you're going to get an echo 2.5 seconds later. And kind of testing your equipment and saying, okay, is my antenna working? Am I sending out a pulse? Is it strong enough? And so we'll push a little button on the ham radio. Deek! 1,000, 2, 1,000, bing, and you get your echo. And so there's your radio waves, and in this case from Houston to the moon. Now, this one is got to be a little careful with. It does ask what the RMS value is. We know this, that if you take the electric field and divide it by the magnetic field, that's equal to C. And that's true at any moment in time. So if you take the maximum, you divide it by the maximum, you get C. And if you take the RMS, you got to divide by the RMS. And so, in other words, for me to solve for the RMS magnetic field, I need the electric field as an RMS. And this clearly said it was its maximum. So to get the RMS, I need to take this maximum, 0.205, and divide it by the square root of 2. That was our discussion back in our AC circuits about the connection between maximum and RMS. Of course, and then I would get the BRMS. I suppose we could use maximum field here and then get maximum B field and then take that and divide it by 2 also. That works just as well. So I'm going to write here BRMS would then be this 0.205 over the square root of 2 divided by C, the speed of light. So 0.205 divided by the square root of 2. Now, I'll take that and divide it by 3 times 10 to the 8th. And so this would be 4.83 times 10 to the minus 10 Tesla. Which sounds incredibly small, and it is reasonably small, but it's really more because a Tesla is such a big unit, as we've been talking about, and not really part of this set of chapters. But if you remember back on exam 2, we did a lot more magnetic fields and talked about the Tesla, how big it really is. And again, not unreasonable to detect, just like, this is 1/5 of a volt. For a 1 meter long antenna. That's very easy to pick up 1/5 of a volt. And this is really just as easy. It may not sound like it because it's got such a small number. In fact, it may bother you that it's so small. I hope that's not the case. And then so E, it says, now, what if these radio waves were entering some material? And so this we didn't quite do in class. But if you read this through, hopefully you'll see what it's going. We did say, talk about dielectric material. Now, granted, that was a few chapters back. But what we said is it would change the electric field. And that's what we have here in our electromagnetic waves, is the electric field interacting with each other. And in this chapter, we said the speed, which would be C, or maybe I should just put V for their speed, would be 1 over the square root of the permittivity and permeability. And both of those were free space. So those were perfect out in outer space. We didn't have any other material around. But this is saying here, it changes. That is, the permeability has increased by 1.75. And so that's just kind of a reminder in case you forgot chapter 26. We haven't done too much with the electrical or magnetic properties of material. But we did have to kind of focus on the dielectric constant when we dealt with capacitors. And so guess I'm trying to remind you of that. And I'm even trying to help you out by it says that is the permeability will now increase by this factor. That is, it was 8.85. Now, if you multiply it by 1.75, it'll be 15.5. Here's my point, that if I put in the 8.85 into here, and the 4 pi times 10 to the minus 7. That's how we got the speed of light in a vacuum. So here, the speed of light, or the speed of radio waves, would change because of the electrical properties. So instead of putting an 8.85 times 10 to the minus 12, I'm going to put a 15.5 times 10 to the minus 12. And then the permeability is the 4 pi times 10 to the minus 7. So the magnetic effect is unaltered. Only the electrical effect. Water, as you know, is polar and does have an effect on the electrical. It also would have a lot of other effects on these radio waves, but this is about as much as we could really digest based on what we learned and as far as we got. Anyways, you could see that the speed would essentially be reduced by the square root of whatever that increased by. So if the speed of light was 3 times 10 to the 8th, it should be reduced by the square root of 1.75, coming up with 2.27 times 10 to the 8th meters per second. And in fact, those of you who've gone through the optics will probably recognize the square root of 1.75 as 1.33 or 1.32, because this is what we said in our optics, that light would be slowed down by what we called the index of refraction. Okay, but anyway, that's only relevant for those of you who've gone through our optics, which is Physics 123. So half of you, that makes sense. The other half, you're probably still okay. But you'll see that then in March when we start up next semester here. But maybe this calculation, I should just do the raw calculation instead of getting a little more detailed and turning into an educational problem. And so let me just do that. Let me just go 15.5 times 10 to the negative 12 for the new permittivity, and then times 4 pi times 10 to the negative 7 for the permeability. Let me take the square root of that, and then finally the reciprocal, and it looks like 2.27 times 10 to the 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Yep. And so there it is. So I hope this one wasn't too challenging for you. I think I will count it a little low compared to the equal of these 4. Just, not that you can't do it. And if you did get it, I hope you're happy with yourself and proud. But I didn't really want this to be a hard problem. But I think this is a fun one to think about. In either case, that's it. I hope you got everything right. That would be ideal. But anything that was a little confusing for you, hopefully the video kind of explained it, and now it makes sense to you. And you'll be that much smarter moving forward and never make those mistakes again. All right. Take care.